Okay. Well, we're here to discuss a little bit of what we saw in the video. There are a lot of really great videos that show what scientists do, and we wanted to pull one out that would be an example of something you could show your kids in the classroom that would exemplify a lot of those traits that scientists have, curiosity, etc., and some of the skills that they utilize on a daily basis. So we're going to look at another one later on that will tie in some more to what we're going to be looking at. But we're here to talk about data modeling. Now, just to kind of let you know who I am, it was interesting to listen to the introduction as Eric was talking about teachers and educators. I still consider myself a new educator. This is my 5th year, and I was fortunate enough in my district to have been sponsored by Helios, thank you very much, to be able to go to the SLI this summer with NSELA. I was an NSELA member a couple of years ago when my district science specialist, Vicki Massey, said, hey, you should be a member, and so I joined. But I let my membership lapse. That won't happen again, especially after having gone to the SLI. One of the pieces that we talked about quite a bit during the Institute was data modeling. And what does that mean? What I'd like to do is kind of give, first of all, recognition to Richard and Lair and Leona Schaubel, who they were the ones that came and presented to us at the SLI and talked about their research in students and learning representation, learning about modeling probability and such. It was a very dense presentation. They did a fabulous job. A lot of us, when we go to something like this, we're looking for something we can take back to our classrooms the next day. Where's that copy that I can make and hand to my kids? Theirs was not about that. It was about this new process, thinking about working with students and large sets of data and helping them to come to understand those concepts that go behind what they are so used to doing in an automatic fashion and what that really means. So they did a fabulous job, and I thought to myself, how can I take this back to my classroom? How can I apply this in my own classroom? And that's what I'm going to show you. I'm going to kind of go through real quick what they brought to the table at the conference, and then how I applied it in my own classroom. So that's just a little snippet there. Really, one of the things that this is all about is building mathematical representation. So when we talk about data modeling, it's building a mathematical representation of some natural phenomenon. And they have this fabulous adjective there, or a verb, whatever that is. I don't teach English. Mathematizing nature, which I love that word. And that's what we're trying to help these students to understand. Scientists, we want to understand nature. You look at Galileo, he said that math was the language that God wrote the universe in, and so math is the language of science. And so bringing those two together, mathematizing nature, that's what we try and do as scientists in order to understand it. And it's really based on the way scientists work. So as I started to look at this and look at what the kids thought, I found that I need to understand a little bit about what they already knew. What are models? And so I use a tool, and I'm going to subject you all to a little bit of what my students got to go through. I'm going to give you a little piece of a probe called "Is it a model?" Okay, so that's the question I'm going to give you in a moment. And we're going to set up a little poll here, and everyone's going to get to vote. So Carolyn will help us out with that piece, I'm sure. But this probe comes from one of the volumes of Uncovering Students' Ideas in Science by Paige Keeley from NSDA Press. So I used this with my students because I wanted to know, what do they already think? So we're going to set that poll up here for you guys right now. So Carolyn, you can send that out. Mm-hmm. So here's the question for you. The student version said something along the lines of, which of these would you consider a model in a science classroom? Okay, and then it had a number of different categories to pick from. What I want you to do is, which of these would your students least identify as a model? Okay, these are all types of models, but which would you think that they would least identify as a type of model? I wish we could hide those votes so that people don't vote with their friends.
There might be a way to do that, but that's beyond my my expertise right now.
Oh, actually, do we have to hit broadcast results for them to see it?
Well,
down on the bottom.
Yes, you do.
Okay. All right.
All right, we're going to close the poll now. And now we should see the results. Yeah, okay.
All right. Well, you guys did really well. Maybe the title of our presentation gave it away. But we're going to take a look at, can you guys see the results there?
No.
No.
Oh, that's what we have to click the button. Sorry. Here you go.
Broadcast? Yeah.
Have you got
Got
it
it
graph
now.
now? Okay.
Yep.
All right. So you guys did a nice job. We'll see. That was the #1 lowest on the questionnaire for the students. Okay. And we'll see how you did on the others. We had 15% said graphing the speed of a car wouldn't come out too well. Watching a simulation came out pretty well. Forming a mental image of molecules in liquid state, people picked that one. Okay. All right. Thank you very much, Carolyn.
Okay.
So you guys kind of have a finger on the pulse of what you think the students might be looking at. I wasn't sure what to think. I figured some of those would come out that way, but I was pretty surprised by really what I came up with. And here's just a couple of them. Okay. So is it a model? My students, for building a paper airplane, 100% of them said yes, not a problem. Demonstrating day-night cycle with a globe and a flashlight. Again, did really well. 97% said yes, that's a model. When we come to mental image of liquid molecules in a liquid state, for you guys, this was the second worst ranked, right? For my class, it came out at about 91%. Now, we had already done kind of a nature of science black box activity and talked about mental models, so that could have skewed my results. This was just with my 3 classrooms of 8th graders. Okay. The next piece I looked at was watching a computer simulation of a hurricane. This one also scored fairly well. This happened to be just around the time of Irene, so we had had some discussions about that. Now, graphing the speed of a car, this is where you guys started to kind of differ from the poll results here. What I ended up with was 33% said yes, that was a model. So 67% didn't believe that was a model that would represent something in real life in a scientific sense. And the last one that I had was developing a mathematical equation to solve a science problem. Only 26% of the students thought that that was a model. Now, I started to think about this, and of course there were a number of other questions in there. Some of them were not models, visiting the Grand Canyon, etc. So if you'd like to look at that, check out Paige's book. It's fabulous. But I started to look at this and I thought, well, what is the problem? What's the disconnect here? They could visualize that visualization of the liquid molecules was a model. They got that. But all of a sudden we started to step further away and lose some of that connection. So what I wanted to look at was, well, I think some of the ideas that came to mind were that they were more detached from the phenomena. The graph did better than the equation because the graph is a physical thing. And that's what a lot of the kids said when I asked them why. Most of them, they thought a model has to be some physical thing. When pushed on that, when I pressed them on the question of, well, how can you say that, visualization of molecules is a model, whereas these ideas, such as an equation, were not, they started to fall apart in their reasoning. But I think being detached from the phenomena is an issue. Also, the students have very little experience, generally, generating data. When I say that, I'm speaking of in the math classroom. A lot of times in the traditional math classroom, they'll get a set of data. They have the X and the Y already in the T-chart, and all they have to do is make the graph. And that's the last piece. That graph is very often the end product. The evaluation in their classroom would be, did you correctly represent those data points on the graph? There we go. We're done. And there's not the next step of utilizing that model to make a further prediction, etc. So I thought, well, how would I be able to help this situation? So I started to look at it, and really this comes from what Rich and Leona had told us at the SLI. We need to involve the students more in data collection and use. And I know I'm not going to do them justice to their presentation, nor to their book, if you look at their book, which the reference is at the end of the presentation. But there were 4 big ideas that I came away with from the SLI. And the first one, to get students more involved and to use, and we're going to refer back to these numerous times, is having the students define a problem or the question. Having them do that definition, because data doesn't have a structure or a form except in that it helps to answer some type of a question. So the way you're going to use the data depends on the question. So students need to be involved in generating that question or the problem. They also, many times, will have to determine how to measure this phenomenon. It may not be something that there's a measure just readily built for. And we can talk about that as we look at my example. I'll mention a couple of pieces of it. All right. So they may need to determine methods to measure the phenomenon. They'll also need to be intimately involved in choosing the means for representing their data. Because remember, they've come up with the problem or question. They know what their data is supposed to answer, how that's going to answer the question. And their data has to be structured, in a sense, in the way that will represent the best answer to it, or communicate that answer that they're trying to get to. And the last piece is using their data to support their position. Did they really answer that question that they had asked originally, and does this data do it in a logical fashion? And it's this idea of argumentation. And we're not going to talk about argumentation much in this webinar, but there was quite a bit of that in the SLI. So let's take a look at just what I did in my classroom. I thought, hey, I need something that I can do with my kids in an 8th grade advanced science classroom, where it's essentially the portion that I was focusing on was the physical science. And my class is interesting in that my 8th graders range. We're kind of a magnet school for our school district. And I have in my classroom from pre-algebra all the way up to honors geometry. So it's quite a range in math skills. So that's just kind of a little bit, as you start to look at these graphs, you're going to see a lot of variation. But it didn't really matter which group those kids fell into, although some of them you will identify as some of my honors geometry kids. But so the first thing we did was we asked the kids to kind of define a question. Now, I prompted this because, again, I was driving the activity, or at least introducing it. I started it out as kind of a team-building challenge. And what I wanted them to do was I wanted them to build a boat that would hold 100 pennies. And that was really the instructions that they were given. Your job is we're going to do a little activity today. We have about 20 minutes. You guys have to build a boat that can hold 100 pennies. I picked this because after the SLI, I started reading more of Taking Science to School, and there was a snippet in there that referred to the fact that if we can involve students in an engineering task where they have to optimize something, they become more aware of the variables that are involved in that. And then if they go into an experimental task, they'll have a more intimate understanding of those variables and how they can control them. So my goal was to introduce, eventually, buoyancy and have the students calculate that and come up with an equation for it. But I wanted them to first have an exploration, so 5E as well. So this is kind of the engage piece. So our question became, what is the best boat design to hold 100 pennies? And this was going to drive, essentially, their data collection and their representations and everything else as we see. So what's the best boat design to hold 100 pennies? And they got some materials. 1 piece of aluminum foil, 2 straws, and 10 centimeters of tape. Okay? So students started building their boats. Again, like I say, they had about 20 minutes, maybe 30 minutes to build a boat. And then this was at the end of class, so the next day we began testing. And they had to come up with what they were going to measure. Now, part of it was already given to them, right? They were going to have to count the number of pennies. Okay, so that was one. That was just a kind of a given. The other piece was, what does this mean by best boat? And I didn't really say much other than that. So it was up to them to determine what that meant by best boat. So as we began testing, we had a tub and we were placing the pennies in there. I put it up on the dot cam so everyone could see it in the room without having to huddle around the table. And each of the students came up, tested their boat, or they were working in pairs. they began collecting data, and here's just an example for one of my students' notebooks. So some of the things that had been handed, or as they came up to test their boat, they presented to the class some of the information. One of the things that, like I said before, was the first thing that everybody was really concerned about was the number of pennies. But some of the other information that was provided to them by the builders of the boats was an example of the design. And this one you can see some people wrote down, oh, the shape was square, or it was triangular shaped. One was a canoe shape. Okay? So they made note of the different shapes of the boats, thinking that might be one of those characteristics that is important in being best. They also made note of the usage of the straws. So the straws were on the inside, or they were on the bottom. Some of them had straws around the perimeter. Okay? So they tried to take in as much observational data as they could. The other piece that was provided to them was the dimensions of the boats. So that was one thing that, as they were writing up their procedures, I did after they had their fun building the boats, said, now you have to write your procedures, how you built it, so someone else could copy it. One thing they needed was a diagram with their dimensions. And then we also calculated the volume of each boat. All right. So the students had all this data. They had, for each class, between 8 and 12 boats. 3 classes, so I ended up with about 30 boats. So I said to them, after they had collected all their data, after all their testing, I said, now what I would like for you to do is that third step, like Leona and Rich had talked about. They had already come up with a question. They had already done some measuring of some sort. And now their job was to represent their data. So what we did was, I said very openly, I said, I would like for you to represent your data in a new way. Not a lot of guidance on it. And some teams kind of worked together and had very similar representations. Other teams, you know, I could see some students were kind of mulling it over a little bit more. Well, what is important? What is most important in this question of the best boat? What do I want to represent? Obviously the pennies are involved, but what other factors? I have a number of different pieces of information do I want to alienate? And so the other instruction I had given them was it couldn't be the same type of representation. So it couldn't be just another data table. So some type of visual format. Some students seemed to have a little more difficulty, and so as I was circulating the room, if I saw that they seemed to be stuck, I'd ask some things. Well, what do you think is important here? What seems to matter? And a lot of them would pull out different things like the height of the boat, or maybe the surface area of the boat, or the the length of the boat seemed to be, or how the pennies have been placed, etc. So, again, what seems to matter? So here are some examples of what they came up with. This is very typical of the majority of what we had done. And so we're going to go through a number of different graphs, and we'll see some styles here. This one, like I say, is very typical. Bar chart, one of the 3 types of graphs in the world that the kids love. In this case, it's ranked by number of pennies, and along the bottom it just has the groups. Okay? A lot of kids did this. The next one, she also did a bar chart. This one it's really messy to read. In fact, we shared graphs with one another, and this is one of the ones that I actually put on the projector, and I said, what do you guys think of this graph? And they said, it's kind of hard to read. But what she's doing here, she's trying to make sense of these different factors that she thought might relate to this idea of best. So you can see in the first portion up above here, she's got some color coding, shape coloring that she wanted to represent the shape of the boat. Okay? She thought that might be significant. Rectangular, square, circle. Okay? Others, she also thought, well, I think the straws might be involved. Let me see if there's a relationship there. So she kind of started including the, straw usage. And then, of course, she did kind of a range type thing on the height of the sides of the boat. She thought that was a factor that was important. Okay. I didn't highlight it, but if you look over on the left-hand side there, you can see that she says, this shows that boats with sides and corners, so, you know, rectangular or square, straws on the bottom, and a height between 2 and 6, and she didn't finish her sentence there, but seemed to be the best boats for holding the number of pennies. So avoid circles, wrapping straws around the side, and high heights. If they got to be too high, the students started to see that there were problems with the boat. Okay, so here's another one. Again, this is very similar to the first one. We've got group numbers, we've got number of pennies on the side. However, this student thought, you know, that's important, the number of pennies, because that's our question. But there's something else important here. And she decided, I'm going to do another graph that shows the group numbers compared to the volume. And so in our minds, we say, well, yeah, those do seem to be two of the more related pieces. If she had them in a single graph, she might have been able to see a little bit more, you know, easier recognition of those relationships. And that's what we get in this one. This student decided, hey, I've got volume, and I've got number of pennies. And while this is not a perfect use of the graphing techniques that we would anticipate, they were at least trying to kind of start putting these ideas together, what the relationships might be. So those are typical of what we started seeing. There were quite a few who actually looked at the volume compared to number of pennies. This one I thought had kind of a rather interesting approach to it. What she did is she did sort of a histogram average type thing. So she, for my graph, I did 3 different ranges and then the average number of pennies in each range. So she took those boats that held pennies, or the volumes in those ranges, and then averaged the number of pennies that they held. And you get an actual really good representation of that relationship in this case. Okay. And here's what we would all expect, or what we would be looking for to show the representation. And this is, you know, like I said, one of my honors geometry kids. But so he says, with this, you know, scatter plot with a line of best fit, almost a clear correlation of volume and the number of pennies. Now this one's an interesting one because his table group, a number of them did this together. This classroom had a student who, while they're testing, they decided, hey, I'm going to put my pennies in really fast. And I wasn't watching too closely, and the boat sank, and they said, yes, we got 250 pennies. And I thought, no, I don't think that's quite right. So if you look over here to the volume between 100 and 150, up about 175 is where their data point is. And I told them, well, I don't think you got 250. Why don't we call it 175? And later on, the students in the class said, Mr. Jones, we can tell that Chad cheated. He's become famous now. Because his doesn't fit anywhere near the line of best fit. And so they were able to use this to show that Chad did something wrong while he was testing his boat. Now, these are not the best representations, not what we would expect as kind of the final or best way of looking for the relationship. But what it does show is it shows the students struggling with these ideas, struggling with the idea of how do I relate these variables and how do I come back to that question I had or the measurements that I had to come up with for the idea of best. What I did was, after they had each had a chance to construct their own graphs, they had to come up with some reasoning. And I asked them to use their reasoning and have kind of a data discussion. So since some of the teams had worked together on their graphs and had similar representations, I mixed them all up. So I took one person from each group and put them into new groups and had them do a data discussion. So we did this kind of as a, everyone stood around, held their notebook, shared their data, and we had a couple of questions that I wanted them to guide their discussion. Why did you choose to represent your data this way? So what was the purpose in it? And does this representation fulfill the goal that you thought you had? Sometimes they found that, well, I was trying to show this, but my graph doesn't really show it that well. Or I thought this was what was important, but now that I'm looking at it, something else looks more important to me. So this was always going back to that original question. How does the data answer the original question? Again, data only has structure depending on the question that it's trying to answer. And this data needs to be structured in a way that we can see those relationships. So that's what I was trying to get them to do, and to look at one another's graphs and see how people had done it differently. Now, we did this in small groups, so not everyone got to see everyone else's notebook, but I did see it show a number of these slides that you've seen. I showed them to some of the students, and we discussed some of the benefits of each of those and how they could have been improved. So here's some of the reasoning that the kids had after. So here's some conclusions or some of their analyses afterward. And one thing that I would want to point out here, so this one, she thought that surface area made a difference. And she's got a diagram there showing how surface area, you can hold more pennies, etc. And we know that surface area and volume will be related. And we'll look at that in just a minute as we look at some more graphing tools. But this student said, I hypothesized that boats with high sides was the best model to float 100 pennies. My hypothesis was rejected because, from what she saw in her data, the more surface area in a boat, the more pennies it could float. So some had really high sides, but not a lot of surface area on the bottom. And those high sides, as we discussed later on in a class data discussion, seemed to collapse earlier. So we had some structural failures that became a part of our discussion. Another student started looking at hers, and one of her conclusions was that boats with bigger volumes normally did better, but then again, the smallest boat did the fifth best of all the boats. So we've started to look at the data, come up with ideas related to trying to interpret their own information and answer the original question. Now, the students had, like I said, about 10 to 12, pieces of data for their classroom. All right. I took all the classes together and I put them all together into a little spreadsheet, and I shared that with the class. Now, what we're going to do here is we're going to switch out, because I started to use in the class discussions a tool that we were given at the SLI, Tinker Plots. So what we'll do here is we're going to switch over to a screen share. And I'm going to show you kind of what this tool can do and kind of talk about what I saw it valuable for. Do I need to switch that, Sherilyn? Yeah, I'm going to just switch over here.
Now go to your layout. Yeah, you got it first.
Okay, give me just a second here. We'll see if my desktop is clean. Here we go. All right, so I had given the students some data. And here's the data from all the classes, okay? And what I did was I brought it into this fabulous tool that we were shown called Tinker Plots. Now, this was co-developed by a number of different researchers, but Rich and Leona were two of those that were instrumental in some of its development. It comes from Key Curriculum Press. We were given a temporary license that was good for 30 days or a week or something like that. When I was at the SLI, I think even the first night, as soon as I got my next check, I put the $50 down. I thought, even if I can't get a license for every one of my students, this is something that I can use and that would be valuable for me in showing some of these ideas to the students. So what I did was I imported that file, okay, all this data, I imported it. And what Tinkerplot does is it creates kind of a, let me turn on my little highlighter deal here. So what it does is it kind of creates a deck of cards with the data sets, okay? And it's a neat tool in that you can build plots really quickly. So what I did was I said, hey, here's your data. And of course I did some of the fun stuff where you can stack things, and I highlighted over here, I highlighted the number of pennies, and it changes colors. And I asked the kids, why do you think they're different colors? Oh, it's probably because some have more or less pennies they held. So we did a little stack, and they oohed and awed, and I said, oh, well, let's put this in order somehow. And, oh, wow, that's cool. And we were all wowed by that as well. I didn't really understand the power of this tool until I started to use it in this activity with my students. And we said, hey, let's take a look at what we thought was important. Why don't we look at pennies, and we'll put this down here. And it really quickly will, separate things out, okay? And that's neat. And I can even do something like this. I can drag it across, and I get kind of a frequency table, frequency chart. Okay? And we said, well, what else do we want to look at here? We could look at something like volume. You know, oh, that's cool. Or we could look at the height of the boats, right? And this was all interesting to the kids. And I said, well, what if I did something like pennies and I compared it to something else? How about I compare it to pennies? What would it look like? They go, oh, well, that should be a line. And if I drag this right, then yeah, sure enough, we get a straight line because it's a direct correlation. What we started to do is, in a discussion, I said, well, what variables do we think we want to look at? Pennies was one. Okay, that's our question, part of our question. And let's look at, well, height. Some people thought height was important. So I quickly just drag over height, and the dots just pop over to where they need to be. Now, we had a discussion here. How do you think? Does this look like those are related to each other? Well, maybe. Well, let's look at, I don't know, width and see if that looks any better. And just compare some variables, one to the pennies, you know. Each of these variables in turn to pennies. And that one doesn't look too good. There's a big chunk that kind of is over here, and a lot of them have a lot of different values for pennies, but they have the same width. That doesn't look good. How about if we looked at length? We just dragged each one of these, and the kids told me, well, I don't think that looks very good either, because we have the same number of pennies for all these different lengths. That doesn't seem very good. And we had, one of the kids said, well, what about area? I think the area matters. So we created a calculation for area, and we looked at that. Area looks okay-ish. You know, there's kind of a clump here in the middle. There's not a whole lot that are, you know, it looks better than any of those others. And we grabbed volume. Oh, that's starting to look a little bit better. So we had a discussion about which of these looked to be kind of the best clumping. Now the reason I liked this was because you could do, what, 5, 6 graphs in a matter of minutes? Whereas if I gave those kids 30 data points and said, why don't you graph each of these variables and see which one of them has the greatest relationship to number of pennies, that would take them forever. And yet with this, we could dynamically, and I happen to use a smart board, but you could easily just use this with a projector and show it. But we could drag these variables around and really quickly see the relationships. So what I ended up giving them was I gave them the scatter plot, and I gave them the data table. And I said, what I'd like for you to do is I want you to see where the best relationship is. What's the line of best fit? Some kids knew that term, some didn't. So for those who didn't, we had a discussion about what that meant. And we had a reference line here. And then I had them tell me, after they had done it on their own, where do you think that should be? And almost everybody came out to something along these lines. And we were able to take a look down below, and for some of them, this looked very familiar. Whoa, that's the y-intercept formula. And all of a sudden, these ideas started coming together about how this idea of a line of best fit could be useful for us, and what the relationship was between the variables that were the best. Now, this wasn't the original question. What's the best volume for the most number of pennies? Well, we didn't ask that. We asked, what was the best boat? So some of the kids, when we started getting to this, said, well, that doesn't answer our question. I said, well, you know what? I think we pretty much answered the question, didn't we? We want kind of a big boat with pretty good sides. We want a largish volume, and we want it kind of square. And the kids were, yeah, I guess that's true. That is kind of what we came up with. Once we had this data in this format, we could have quite a discussion. Now, you know, I'm noticing, what is the next idea here that we can talk about? Why is there so much variation here? And that's what one of the kids said. She said, well, I see a lot of variability up here in the higher volumes. Down here in the low volumes, everything's kind of clumped together. Why would there be more variation in the higher volumes? So we had a discussion about that in the structures, and some people said, yeah, the sides collapse more. So we started coming up with ideas for what would these errors be, or what might have been problematic. And then the question became, what's the next thing we can do with this data, or what's the next question we can ask? So we're going to go back to the slideshow now.
Okay. And Bruce, just call your attention to the time.
Okay, yeah, I'm finishing up here. All right, so
They'll load in a second.
that's okay. But it's really that next piece. what do we want them to do with the data? We want them to be able to ask the next question. In my mind, science isn't always about answering the questions, about asking the next question. So that was the next piece to use. And this is where we have to use, we're stepping beyond those 4 pieces that Rich and Leona had given us. But really, this is the next step, extending to new uses or new questions. So I asked the students, hey, what can we do with our data? For instance, that line of best fit, now that we've got that, can you use your graph to predict the volume that's needed to hold 300 pennies? Some students had asked things like that. Can I build a boat with a volume less than 1,000 and still hold more than 200 pennies? That was some of the questions. And then, after looking at the data, what new questions could you ask? So we started to think, hey, what's the next question? What's the relationship between volume and the mass that it can carry? So the students have actually started designing a new lab with new materials. You guys are not muted, but they're probably not listening anymore. So real quick, the last couple things that I have is some suggestions for data collection. How could you extend this into your classroom? I just tried to give an example. I'm more than willing to be discussing this on the NSELA website and such. But some ideas that I came up with, anything that you do that involves quantitative data, if you've got numbers involved, you can probably model it. If you've got something that they need to develop their own measures, that would be a great place to bring this in. Can you take something that's, qualitative and make it a little more quantitative and then use that to build some type of a model? And then there's lots of ready references for data collection. There might be labs that you already have. If we have time, we may see something on Teacher's Domain or on PBS Learning where there's some great lesson plans that are already there. There's some on using materials and data collection. But I had come up, there were a couple that we were introduced to at the SLI, the Beguile tool, the Galapagos finches. We saw that, and this is a great simulation if you're doing natural selection or looking at evolution. And another one that's along those lines also, because what I demonstrated was a physical science, but there's a lot of things out there for biology as well. This is a great tool that we also played with at SLI where you can get data and then use that to support your argumentation and your question and answer that you came up with. And again, here are my references. Like I said, I've already actually started under the SLI discussion thread. So please post any lessons that you have or ideas that you have or questions you might have, and that would be a great place for us to start a discussion about data modeling and how you might be able to use it in your classroom. Again, I'm not an expert. I was just somebody who was enthralled by the presentation at the SLI and sought a way that I can incorporate it in my own classroom and help my students also improve their math skills and tie in between the math and science. And I haven't talked about that, but almost daily my math teacher and I, we talk about it. Today they actually use this data to plug into their graphing calculators and get a line of regression for those students who are in the geometry classes. So a skill that they're going to be using throughout their math careers, and yet this was data that they had generated and had meaning to them. So bringing that back so that they're not as far detached from the phenomenon that they are representing with their math. And that's pretty much all I have. If you guys have any questions, please shoot me. You can always shoot me an email. I didn't put it on there, but you can contact me through the NSELA website on the discussion board.